We are members of SKA Robotics, part of Student Space Association of Warsaw University of Technology, and for the past year we were hard at work developing and improving our Mars rover series. The team consists of 33, mostly undergraduate engineering students, divided into 4 sub-teams: mechanics, software and autonomy, electronics and science. Work is conducted on weekly meetings, and platforms such as Discord, Trello and Git provide seamless collaboration on all levels. Depending on stage of the project, our work is summarized monthly on progress meetings or field tests.
From the beginning of the design process, simplicity, low mass and robustness were key factors. This is why we used four-wheel construction with aluminum frame and rockers, as well as modular PVC electronics enclosure. Motors hidden within each of the custom wheels, combined with a simple suspension of our own design, allow us to keep a low center of mass and high clearance to easily manage rough terrain and steep slopes. The 5-stage Manipulator is capable of reaching over 1.5 meters and lifting up to 5 kilograms. Its movements are registered by a set of encoders which will be used in the implementation of inverse kinematics. A mock-up panel for tests and mission simulation was created. We designed tools dedicated for different competition tasks, such as turning screws and typing on a keyboard. They are transported in a special container on the rover's mobile platform. All design was aided by a usage of software such as SolidWorks, ANSYS Workbench and MATLAB. Most parts were manufactured in our workshop, equipped with basic tools and 3D printers. Tasks that required greater precision or specialized tooling were ordered in private companies.
The RoverSoft consists of 2 main parts. The first one, that we call RoverSoft, runs on the onboard computer and controls the rover. The other part provides a rover controls interface that creates an intuitive environment for the operators. It allows for precise movements of platform, manipulator and cameras. During various tests, we developed a camera's layout that gives the operator a good spatial orientation. Over the last year, we decided to upgrade our autonomy system and implement it using the robot operating system. As a part of its design, we prepared graphs showing the exact structure of the ROS nodes it consists of. Our system uses data from encoders, a gyroscope and a GPS sensor to perform the autonomous traversal task. Together with a given landmark and the shortest path search algorithm, the system will calculate the quickest route to the destination. We have also implemented ultrasonic sensors and a stereometric camera to be able to avoid and maneuver around obstacles. The artifacts are detected with the help of deep neural networks that categorize detected quadrangles as opposed to a traditional image processing approach.
The electronic and communication systems were designed with modularity, scalability, and redundancy in mind. The rover is powered by lithium-ion batteries. A kill switch separates all power sources via contactors in main power and logic circuits. Sirius is controlled by 2 NVIDIA Jetson computers, communicating with ground station using 2.4 and 5 GHz off-the-shelf Wi-Fi communication systems to achieve redundancy and best possible reliability. We have tested our communication system in the field and its performance meets our needs. The onboard devices are controlled by Arduino microcontrollers embedded in custom circuit boards. Currently, we are in the process of implementing STM32 powered boards. A new container has been designed for the new electronics. It consists of 2 modules, one for the power system and one detachable containing all the rover logic boards.
Science module includes onboard laboratory with 4 liquid tests that detects characteristic particles of extant and extinct life forms. The science module is fully integrated with the rover. After the lifting of the drilling device, we can lower a sensor arm into the drilled hole to measure temperature and moisture of the sampling place. We are able to store and analyze up to 4 samples. The chemical composition of the rock samples can be determined by the use of diffractive optical spectroscope. As we use hazardous chemicals, safety, especially the no-spill policy, is our biggest priority, so the injection device is very precise and hermetic.